But so the topic is derivative of inverse trig function. ITF stands for inverse trig functions. Okay, let's start with y equals the inverse sine of x, like so. Well, how we read this? We read it, and the equivalent statement will be x has to equals the sine of y. Okay, what the inverse does, the inverse, given the function of the trig function, given the value of the trig function, in this case y, in this case x is the value of the sine function, y will give you the value of the angle or the argument of the sine function. Okay, so in this case y will be in radian measure, and x will be a value between -1 and 1. Okay? Now, recall that we do have an issue with the sine function. The sine function, over one period, one cycle of the sine function, is not invertible. It's not one-to-one. The reason we cannot say that for each value of the output there is only one value of the input. It's a function. For each value of the input, we have only one value of the output. But if you plot one period of the sine function, like so, from -pi to +pi, okay, you can see that this function passes the vertical line test, therefore it's a function, but it failed the horizontal line test. It's not one-to-one, or it's not invertible over this domain, over one period. It doesn't matter if we go 0 to 2 pi or we go -pi to pi. And to overcome it, what we did, we're going to cut it like so, from -pi/2 to +pi/2. And we're going to say that if we restrict the domain of the sine function right here on this interval where x, or in this case y, because remember the input of the function is y, so we're going to let y be a value between -pi/2 and +pi/2, then at this point the function is invertible, a one-to-one and invertible, and the inverse exists. So we're going to say that the domain of the inverse function of the function x equals sine y is -pi/2 to pi/2. And this is something you learn in trig. Okay? Now, instead of, we want to find dy dx when dy is the inverse sine. So instead of dealing with this, which we don't know, we're going to take the function x equals sine y, and we do implicit differentiation. Okay, so remember, we want to find an expression for dy dx, or d dx of the inverse sine of x, like so, right? Because y is the inverse sine of x. Instead, we will implicitly differentiate the equivalent statement x equals sine of y. Because we know that at the end we're going to end up having dy dx. So So d dx of x equals sine y. Now we have 1 here. And first we take the derivative with respect to y, and then we'll do dy dx. So it will be cosine y dy dx. So dy dx equals 1 over cosine y. So far we're good. Here's the problem. I need to get rid of the y, right? Because I want to find an expression, I want to find dy dx without the y. So first I'm going to replace cosine y with the sine. And we know that cosine squared plus sine squared equals 1, the first trigonometric identity. Therefore cosine y by itself will be plus or minus the square root of 1 minus sine squared of y. Okay? Now, what is sine y? Sine y is x. So it will be plus or minus the square root of 1 minus x squared. By the way, this trick going to use a lot in Calc 2. That going from algebraic expression to trig expression back and forth. But now we have an issue with the plus or minus sign, right? But remember, what we are equating, we're saying cosine y equal this thing. Now, we are working on the interval negative pi over 2 to positive pi over 2. In other words, we are looking at the first and fourth quadrant. Folks, what is the sign of the cosine in the first and fourth quadrant? On the right side of the unit circle, what happened to the cosine? It's always positive. Okay, and with this, we're going to say the following. So we're going to say, however, cosine y is positive on the interval negative pi over 2 comma pi over 2. So therefore, cosine y going to equal only the principal root, only the positive. Okay? And now we are ready to say that dy dx equals 1 over positive square root of 1 minus x squared. Like so. Okay? Or, now we can say that d dx of the inverse sine of x, the derivative of the inverse sine, is 1 over the square root of 1 minus x squared. Okay. Now, similar exercise, similar procedure leads to the following. D dx of the inverse cosine of x will be negative of the same thing. Okay. What about the tangent? The tangent, I'll just give you the tangent because you need to know it, but what you said is incorrect, JT, because the tangent is sine over cosine, but the inverse tangent is not the inverse sine over the inverse cosine. It's not the same. Okay, so what about the tangent? A different procedure, it's not similar, but a different procedure leads to the following. D dx of the inverse tangent of x. This is easy one to remember. and therefore it's used a lot in calculus. It's 1 over 1 plus x squared, like so. So these two, so now we have three, the three primary. Okay, I'll leave it at that. So I gave it the second and the third free. In other words, I didn't prove it, but maybe I'll do it on Friday. Okay.